As you see here, this project is about developing a reference machine vision system for lane detection, which is a part of advanced driver assist systems or ADAS. And this can be useful for both human-driven as well as autonomous vehicles. So before we go into the presentation, we have three members core members who worked on the project. Myself, Adam Pike from Texas A&M Transportation Institute, and Abhishek, who is going to present the work. The materials for this project was provided by 3M, and they also provide a lot of guidance throughout the project in terms of the directions, research directions, and other things. This project, so first we want to also thank Safety for supporting this project and our research, and we also thank the administrative team at Virginia Tech and TTI, which includes Sue Chrysler, Elissa, and Eric, for all the help that they did throughout the project. So now let's actually go into, can you just, yeah. So, before we talk about the research objectives, I just want to lay some groundwork here. Lane markings are an integral part of road infrastructure, at least for the foreseeable future. The lane departure warning systems or lane following systems, which is part of many of the vehicles currently produced, is key part of ADAS. And studies show that lane detection systems in particular have a potential to actually mitigate hundreds of thousands of crashes, and there are a few reports on that, and one of the reports is mentioned here. So despite all the potential benefits and all that, there are still open questions that needs to be addressed. So we are in this project, we are at least attempting to address one of those questions. Let me just first, before I lay out the objectives, I'll just talk about what actually a lane detection system consists of, and then what challenges we have. So in a lane detection system, it really, in general, it has three parts to it. It has a software part, the hardware part, and the infrastructure part. The infrastructure part really has all your markings, your striping processes, your pavement type and lane geometry and all that. Your hardware is the type of camera you use, and its characteristics. And you also have the software part, which has always been part of the vision-based algorithms. And there are many different types of algorithms you can use, and you can use camera, you can fuse that data with radar and many other things, right? So a lane detection system really has three parts to it, and those are the three systems. In general, performing lane detection also has many challenges, and your challenges can come from different environmental conditions or different road scenarios or different road vehicle conditions. This is the reason why it's not a trivial problem, and collecting data for all these conditions for different types of road scenarios and traffic situations it's not straightforward. It requires a lot of both labor work as well as research. Now, in this project, what we are focusing on is to develop a reference vision system that tries to understand the correlation between lane marking characteristics and the performance of the system I talked about, the lane detection system I talked about. Now, there have already been a lot of benchmarks. I mean, people have developed a lot of vision-based benchmarks for different kinds of road conditions and all that. But in this project, we were specifically looking at the correlation between the lane marking characteristics, the different types of materials that you use, to the performance of your vision algorithms. And there have been studies on this, but not that much as what you see on purely the vision algorithms. And so we are evaluating this system as a whole, so meaning that we have different types of material, infrastructure material. We change all those things. We tried couple of cameras, and then we also tried some of the best vision algorithms, and we evaluate the performance as a combined system. So through this project, we developed datasets that can, and we have collected datasets on under different operational domains to evaluate the performance. And we are hoping that this can provide some kind of a baseline for state-of-the-art lane detection algorithms. If you go to the next slide. So the reason why we were looking at these objectives is because we were looking at different types of stakeholders. For sure, state agencies could benefit from using such a system where they can keep or progressively keep track of the performance and the quality of markings. And I've done a couple of presentations in some conferences regarding this work, and state agencies are actually open to this kind of a system, though it's quite hard to get all the data and do the evaluations. At least this is hopefully a start. And from the infrastructure point of view, like 3M, for sure they can evaluate new materials and striping processes against baseline results. And for algorithm developers, hopefully this data set provides a new new avenue for testing their algorithms. Maybe they may want to train their algorithms in different ways, or they can even develop better algorithms to improve the performance, right? So these are the potential benefits that we see in this work. Now, this is just the introduction and the motivation. Abhishek pretty much did all the work with Adam Pike, so I'm going to let now Abhishek talk about how we collected the data sets, what the metrics we used are, and all the other work. Yeah, Abhishek, please proceed.
Yeah, good afternoon, everyone. As Dr. Ratinam mentioned, as a part of understanding how the lane materials actually affect the lane detection systems, we went about developing a couple of data sets that we could use to sort of evaluate this. We did this in 2 stages. The first stage involved us collecting on-road data on the roads in and around Central Texas. So we developed 2 different data sets here. The first one is what we call a College Station dataset. This includes roads in and around College Station area. The second one was a US290 dataset. This includes roads on the Houston Highway, US290. It had a couple of very interesting lane marking patterns that helped us understand better the patterns that are not usually seen on normal roads. The second, in the second stage, we did a closed course evaluation. For this, we got materials from 3M. They provided us panels with a couple of different lane marking materials. We laid them out on a runway at our Rellis campus here, and then we went about doing our lane detection evaluations on them. So talking about the data sets, all the video data in these data sets were collected at around 25 frames per second. We used a Blackfly camera sensor. It was a 5 megapixel camera. We evaluated the data that we collected on 3 different state-of-the-art lane detection algorithms, them being SCNN, LaneNet, and ENet. So the way we chose this was there was a lane detection challenge that happened, I think, in 2018. And SCNN was a winner of this challenge with around 96% accuracy. So that was one of the reasons that we chose that. The second algorithm was basically developed by the competition organizers. So that was another one that we considered. So basically we evaluated the different algorithms using what we call as a F1 score. F1 score is a general metric that the computer vision community uses to sort of evaluate how good the algorithm is. It is a measure. It is a harmonic mean of what we call the precision score and a recall score. The precision score actually gives an idea of how correct the algorithm is performing amongst all the predicted positives. And the recall score actually says how correct the algorithm is amongst those actual positives. So the harmonic mean of this will give a pretty good idea of how good the algorithm is actually performing in terms of doing the lane detections. In this slide, you can see a video of the SCNN algorithm in action. The green lines that you see is the ground truth that we manually annotated. The blue lines and the red lines are what the algorithm predicts. The blue being the true positive, which essentially means that what the algorithm is predicting is matching with what the ground truth annotations are. The red lines are what the algorithm thinks is a lane, but in reality there isn't one. So moving on, we also collect, like, since we wanted to understand how the lane marking properties actually affect the lane detection performance, we wanted to have a measure to sort of relate the lane marking properties with lane detection. So we went about collecting these three data from the lane marking materials. The first one was a QD score. QD is essentially the coefficient of diffused reflectivity. This is what is measured during daytime. The other one is a coefficient of retroreflected luminance, or in simple words, we just call it retroreflectivity. So if you look at the units here, it's millicandelas per meter square per lux. So essentially what these two parameters measure is the amount of light that is reflected from a surface per unit area of the light that is incident per unit area. So that's what we are essentially trying to measure here in terms of these parameters. We also went about measuring the color of these markings using a spectrophotometer in a CIE 1931XY caps Y color space. So this is a standard measure that is used to sort of represent the color of the markings. Talking about the college station dataset, as I earlier mentioned, the videos were collected by driving on roads in and around Central Texas. These roads were a combination of asphalt and concrete surfaces, which had multi-lane and two-lane, two-way roadways. It also had sections with tangents and curves. The pavements on these markings, like the pavement markings on these roads, varied from new to several years old. Some road sections didn't even have pavement markings on there. So it was a good mix of uh, driving conditions, which helped us understand better how lane marking materials actually affect lane detection. We collected data during 3 times of day in the summer of 2019, morning, evenings, and night. This slide essentially shows the material data that we collected on these roads. I'll not spend much time discussing this. We have all these results listed in the final report that we made for this project. So if you are interested, you can look at that report and you'll get to know more. Yeah, we sort of evaluated the data using these three algorithms. We had the algorithms performed really good in some of the roads to really bad in a few of them. What were some of the key observations that we had? So we found that lane detection algorithms performed better overall in the mornings as compared to other times of day. We also observed that roads having higher cap Y and QD values generally produced better lane detections as compared to others. Also, some important observations we had was overall the lane detection performance was slightly lower when we were driving westwards, that is during evenings. One reason for this could be the sun glare uh, that you get when driving westwards due to the setting sun. This an exact opposite trend was observed during mornings when we were driving eastwards. So we see that there are environmental conditions that do affect how uh, that do affect lane detection, and in order to have a better understanding, it's always good to sort of isolate these external parameters. So there is a need to sort of eliminate all these external factors that could affect the study. So factors like sun glare, maybe shadows on the roads, maybe road illumination due to driving conditions and driving roads, like changing roads. There are also factors like different road surface roughnesses, road surface cracks, and ghost markings that we encounter on different roads. So these factors do affect how lane detection system works. In order to have a better idea of what the effect of the lane markings are on our lane detection system, it's generally good to have a single road and have different pavement markings on that road and evaluate it, so that we sort of eliminate these factors. So that's what we did in what we call the 3M panel dataset. We had a couple of panels that the 3M company provided us. So we laid out these panels on one of the runways at our Rellis campus. So we had 4 different materials that we got. We had 2 different the materials came in 2 different widths, a 4-inch wide panel and a 6-inch wide panel. We combined them into 3 sets with 0, 1, and 0.8 forming the first combination, a 6-inch wide 0.2 and 0.6 forming the second set, 4-inch wide 0.2 and 0.6 forming the third set. We laid out these panels on the runway in 2 different combinations. The first one was with 30 feet inter-panel spacing. The second layout was a 40 feet inter-panel spacing. We wanted to evaluate these main factors. So we wanted to know how the spacing between the panels actually affected the lane detection performance. We wanted to know how illumination, that is like whether it's good to how well the panels perform during daytime versus nighttime. During nighttime, we collected data using 2 different headlamp configuration of the vehicle, one a high beam and under low beam. We also wanted to know if there are some interactions due to driving directions. So we did collect data driving northwards and driving southwards. We didn't consider east and west because we know that there is some effect of sun glare that we encounter. So we just wanted to see if we isolate that, would we have any effects due to driving direction. We also evaluated what the performance of the lane markings are depending on how far the panels are from the driving vehicle. So we sort of divided the image into 2 parts. If you look at the image on the right, we divided it to what we call a near field of view and a far field of view. Near field of view was essentially 30 feet from where the car can see the road, and the rest of the markings were classified as far field of view markings. Another factor was just how the panel material sort of affected lane detection performance. By panel material, we essentially refer to the retroflectivity values and the QD values of the material. Yeah, this slide just shows the material data that we collected. We evaluated this the 3M panel data using the SCNN algorithm. I have not included the slide here with the lane detection scores, but it's included in our final report. But I'll just mention some of the key findings that we had. So we observed that lane detection performance was higher in the 30 feet gap configuration as compared to the 40 feet gap one. This trend was observed irrespective whether it was day or night, and irrespective of the panels. So you can see on the graph here on the top right that during night generally we had better performances, and the 30 feet gap ones were better than the 40 feet gap ones. So this was true even for when we evaluated it individual panel wise. Factor 2, illumination. So we did observe that nighttime performance of the panels was better than daytime performance. While the lane detection performance increases with retroreflectivity, we didn't observe much difference. Also, we observed that the low beam illumination was marginally better than the high beam illumination. As you can see here, the one highlighted in red is the nighttime performance. The one in green is the daytime performance. Overall, you can see that the daytime performance was comparatively low as compared to nighttime. This sort of gives us an indication that retroreflectivity scores do matter. Like they are actually a measure of how well the panels reflect light, so they do aid in better detections. The third factor was we wanted to, as I mentioned, we wanted to check if driving directions had an effect on lane detection. So we observed that driving southwards was generally better as compared to driving northwards during daytime. During nighttime, we do not expect there to be any interactions, but we did observe that there was some impact due to driving direction in the 40 feet gap spacing. This was an unexplained trend because like during nighttime, since the roads are just illuminated by the headlamps, we don't expect to see any differences, but there was some impact during nighttime. In our evaluation area based trials, we observed that the near field of view performances were greater than far field of view, and the combined performances sort of fell somewhere in between those two. As you can see in this graph here, this was true both during night and day times. We also, and another important observation that we had was the difference between the near and far field of evaluation was generally higher in the 30 gap configuration as compared to 40 gap. Well, this is a expected trend because since we chose 30 feet as the demarcation area for near field of view and far field of view, there exists some image frames where there may not be any lane marking materials at all. So we do expect the 30 feet gap configurations to have a better performance in near field of view as compared to far field of view. Well, how the panel materials affected lane detection performance? Well, lane markings with higher retroreflectivity generally exhibited better performance during nighttime. Lane detections with 6-inch wide panels had almost the same performance during nighttime, but during daytime, 6-inch wide panels actually performed comparatively lower. As you can see here, 0 to 6 and 0.066 has lower performance as compared to the 4-inch wide panels. This is contrary to what we would expect because like having a wider panel we would think would actually aid in better lane detections, but we did not observe this in our trials. So to summarize what we did, we developed different data sets that helped us understand the influence of lane marking characteristics and other factors that influence lane detection. It is still a continuing work. We are continuing this work in another DOT funded project, which also includes some difficult conditions like rainy conditions. We hope to promote a cooperative infrastructure development. We hope this work will help agencies develop better standards to make roads that are suited for ADAS systems. Our data sets are available publicly. You can go to the safety dataverse and have a look. Our report is also published on the safety website. If anyone is interested, please. I think Eric has shared the link to our report during the email that he sent out. So please do check that out. Thank you.
Thank you, Abhishek. At this time, I'd like to open the floor if there are any questions. Yeah, and there's one. You can go ahead and unmute and ask that question.
Hi, so I'm Samband. I'm a PhD student in the Department of Computer Engineering. So I did not have any specific question. It was just like the presentation was was pretty nice. I just had one question. During the night time, like when the roads are illuminated by light, do materials actually play a role in there? Like for near view and far view, was there were you able to discriminate between them? Like, do lights actually play an important role in there, like on very dark roads when there is no illumination whatsoever?
Thank you for the question, Samman. So in our experiments, we just had the vehicle headlamps that illuminated the road. If I understand correct, you're asking whether the lights that illuminate the road have an effect, and like whether changing the material properties actually have an effect towards improving lane detection system.
Yeah, during the
during night, yeah, I would say yes, because retroreflectivity is an important parameter that sort of determines how well the lane material sort of reflects the light that is incident on it. So having a material with better reflective properties sort of helps distinguish it from the surrounding areas. What I mean by distinguish it is, so the rest of the roads generally appear black during night times. Having a material that actually, sort of reflects light better gives you a good contrast, and this we did find that this generally helped in having better lane detection.
Oh, thank you.
Thank you. Are there any further questions?
Hi, this is Shindi from Dow Chemical. How are you? Very nice talk. So my question is, have you observed the situation that in the nighttime, when the ritual reflection is very strong and the dynamic response of your camera, let's say the dynamic range of the camera is less than the human eye, in that case, do you observe some kind of issue that either, let's say, your camera is saturated in the region of the retroreflection lane markings, or let's say the the details on the road becomes invisible because you have very strong lights coming from these markings?
Hi, yeah, thank you for the question. So we did not actually observe the particular phenomena that you mentioned, because one of the I would say drawbacks of our experimental setup was that if you can see here, we sort of paired two different lane marking materials, and these materials sort of have different properties. So if you can see 01 and 08, they sort of have different retroreflectivity scores. If you see 01 has around 100, 08 is almost say 15 times that of 01W. But when you look at the values here, so when you look at blue and orange, so these are the nighttime detection scores. We observed that even though there was a difference, it wasn't as much as we would expect, because as we see, like 08W has almost 15 times the retroreflectivity score as that of 01W. But that essentially did not translate in terms of lane detection score. What we think could have happened is there is some cooperative interaction between, say, the different lane marking materials. So there might have been interaction such that 01W might have sort of, brought down the performance of 08W panel. On the other hand, we could also argue that maybe 08W could have improved the overall performance of 1W. So the main takeaway is that there could be interactions where, like, even though one of the markings is poor, having at least one good marking generally could aid in better lane detections. So that is one of the.
Yeah, Abhishek, actually, did you see any saturation? Like, meaning, I'm not sure if we exactly tested that, but
yeah, we did not observe the saturation. Yeah, we did not, because like as like in the question they asked, like, we in our setup we did not have one single material which was like, at that level which could saturate the video that we collected. We had sort of a combination of different materials.
Thanks.
Okay, great questions. So again, I'd like to thank everyone for joining the webinar. I'd like to thank both presenters. This wouldn't happen without you guys, so thank you again for putting on the webinar. This webinar will be uploaded to YouTube along with the PowerPoint presentation is going to be sent to everyone in an email later on. Our next webinar will be on data fusion for non-motorized safety analysts, which is set for November 18th at 2 p.m. Eastern Standard Time. Free registration is now open, and you can sign up on our safety website. And those of you who are members of our email list, you will see an email of it pretty soon. So again, thank you, everybody, and enjoy your weekend.
Thank you.
Thank you, Eric.
Thanks.